Hi everyone, this is part 2 of section 2 of chapter 3. Okay, so if you remember, we had Able Baker call center example in chapter 2, and we did simulation of this system in Excel. Okay, but now we are going to have this example in terms of a discrete event simulation. So just for review, this is a computer technical support center, and it's staffed by 2 people, Able and Baker, and we have the solution for interval times in minutes. Here it's discrete, even discrete distribution, and Able is more experienced than Baker, so the service time for Able is usually shorter than Baker, and when both are idle, Able takes the call, and if both are busy, customer waits in queue. Okay, so here actually, if you remember, in Excel we simulated this example for 100 calls. Okay, but here we can do the same. I mean, we can run discrete event simulation for 100 new calls or for a predetermined simulation time. Okay, so again, we need to define the model's components. So same as before, I mean, for the single server, we have the LQT as a state variable for the number of customers waiting in line. So since here we have 2 servers, so we'll have 2 state variables for the servers. One for Able and one for Baker. So LAT and LBT 0 or 1 for the status of the servers. And for entities here, again, we have the colors and we have the servers. But again, since we are not interested in actually explicitly differentiating the customers, so we don't need to define here the entities or attributes. Okay, and for the events, again, here we have 3. Oh yeah, since here we are going actually to assume that this simulation will be ran for 100 new colors. So because of that, we don't have an event here for end of simulation. So because of that, as you see here, we have just again 3 events. If we consider an end time for simulation, then we need to have an event here as E for the end of simulation. But yeah, because of having that criteria for termination, so here we have just 3 events: arrival and departure. So departure from Able and departure from Baker. Okay, and again, same as before, we represent the event notice by this. So we have the event type and the occurrence time of the event. And for activities here, we have interval time for customers, service time for Able, and service time for Baker. And in the dynamic description, we will show how we are going to obtain these times based on the distribution that we have. Okay, and for the delays, again, colors wait in queue until Able or Baker becomes free. Okay, so this is actually the static description of this system. So let's go for the dynamic description. Again, here for the arrival event, let's see what's the impact of occurring an arrival event on the system. So as I said, at any arrival, we need to generate the event of the next arrival. So here, schedule an event, I mean the next arrival event A at time t plus A. So A is the inter arrival time generated by its distribution, and then we add that to current time, which is t, and that will be the occurrence time for the next arrival. Okay, now we check actually the status of the servers. LAT, since Able has higher priority than Baker, so at first we check the Able's status. If Able is free, then this customer will be assigned to Able. Other than that, we will check actually the status of the Baker. So if LAT is 0, then execute step 2, else go to step 3. So in step 2, so here we assume that the Able is free. So we change its status to be busy. And then schedule the departure event at time t plus SA. So SA is the service time of Able, and we add that duration to the current time, which is t. Then t plus SA will be the departure time from Able. Okay, and then we go to step 5. And if actually Able is busy, then we check the status of the baker, and again, if it's free, we change its status to be busy, and then again we generate an event, departure event from baker at time t plus SB. Okay, and if both are busy, then this call should join the queue, so the number of customers waiting in queue will be added by 1. Okay, and then collect statistics and update counters. So this is the impact of the arrival event on the system. Okay. So here we have the flowchart for influence of occurring departure event of the system. So I'll explain one here as an example. Let's say for Able. So when we have a departure from Able, at first we set its status to be idle. Okay, and then we check the status of the queue. If LQT is greater than 1, greater than or equal to 1, this means there's at least one customer waiting in line. Then here, actually at first we reduce the number of customers waiting in line by 1, and then change the status of the Able to be busy, and then again we need to actually schedule a departure event at time t plus SA. Okay, and that's it. And then at the end we compute the statistics and counters, and that's it. Okay. Let's have the manual simulation of the two server model, Able Baker model. So here we assume that we have these numbers, interval time for customers and service time for Able and Baker. Okay, so we assume that there is nothing in the initial status. It's completely free, so there's no customer in the system. Both servers are idle at time 0. So since the first customer is going to arrive system at time 2, as you see here, then there will be nothing from time 0 to time 2. So because of that, we have started the system the simulation from time 2 here. So we have an event at time 2, which is arrival. Okay, and so Able is free, so Able takes this call, so the status changes to 1 from 0, and since it's arrival, we need to obtain the next arrival time, right? So because of that, we need to generate the inter-arrival time for the second customer, and again, based on the data that we have here, it's 2 minutes, so we have 2 here. And also, since we have an activity just started, serving this customer, so we need to obtain its service time, right? So since the server is able, so based on this data that we have here, the service time will be 4 minutes, okay? And this is our FEL, future event list. So the next arrival will be at time 4. The current time is 2, the interval time is 2, so 2 plus 2 will be 4. The next arrival will be at time 4. Current time is 2. Service time for this customer is 4. So 2 plus 4 will be 6. The departure event of this customer. And here we have the statistics. So C is the total number of customers departed from the system. And LQT actually is the number of customers waiting in line at time T, and Able uptime and Baker uptime. So yeah, by having LQT, area under LQT will be the total wait time so far. Okay. So again, as you see here, we actually ordered the events in FEL. So the next event is arrival at time 4. So we advance time from 2 to 4. So the next event will be arrival, and since Baker is free, so Baker will take this call. So Baker becomes busy at time 4 as well. And so since again it's arrival, we need to generate the next arrival time. So the inter-arrival time here based on data is 1 minute, and service for this customer, since it's server is Baker, so it will be 6 minutes, right? So the next arrival will be at time 5. We know that the departure of Able has been scheduled before for time 6, and departure from Baker now is scheduled for time 10. So the current time is 4, the service time is 6, so 4 plus 6 becomes 10, right? And so yeah, actually we update the statistics. There is no customers actually departed system so far, and Able uptime up to here is 2 minutes, and Baker actually is 0, right? Again, the next arrival, the next event is arrival at time 5, so time is advanced from 4 to 5. We execute the event, which is arrival here, and since both servers are busy, so this customer will wait in line. So here LQT is 1, okay? And since again it's arrival, so the interval time for the next customer will be 2 minutes, right, from here, and that's it. So since this actually arrival is waiting in line, so there is no service time for this one yet actually. So again, the next arrival will be at time 7. The next departure will be at time 6, and also at time 10 we will have another departure. So as you see here, if you take the minimum time, the next event will be departure, right, at time 6, departure from Able, right? So here again, time is advanced from 5 to 6 in order to process the departure event here. So for the departure, if you remember in the flow chart, we checked the status of the line. So if the line is actually there's at least one customer waiting in the line. So since the case is here, so we reduce the number of customers in line by 1, so it becomes 0, and Able again remains actually busy for serving this customer. And since it's an activity, so we need to generate a service time for this one. It will be 5, right? And again, the next arrival will be at time 7, the next departure from Able at time 11, and the next departure from Baker at time 10. Again, if we take the minimum, the next event will be arrival at time 7, right? And yeah, and with the same manner, actually, we update the status of the statistics here, and that's it. So as you see, this manual simulation is exactly working based on the flowcharts and the logic that we just formulated. Okay. And as for performance measures, average caller wait time for 100 calls, we can again take the area under LQT and divide this by 100, the total customers. And if we divide the area under LQT by TE, I mean the time of the last customer departed the system, which we call this as TE, then it will be the average, I mean time weighted average number of calls online. Okay, so yeah, that was our second example in section 2, and in section 3 next week we will see more examples on formulating the system in terms of discrete event simulation. Okay, thank you.